Hi, I'd like to introduce to you Jim Lewis.
Hi, let's see. My name's Jim Lewis. I'm the creator of OSVVM, and I'm also the IEEE 1076 Working Group Chair, and pretty much I also do training. So I recognize a few faces here from previous classes. So this presentation, though. Well, are we not on this? There we go. Okay, so this presentation, the essential steps to simplifying test benches, really is going to also look at the bigger picture of what do we do when we're test benching, because I've run into a lot of places where people are like, why, why is there, even in the system Verilog, why is there a driver? Why is there this and that and the other? So, how do we get here is going to be part of this presentation here. I'm going to start out though. My buttons aren't working anymore. There we go. Okay, so there's first a few essentials. We hear a lot about other languages other than VHDL, System Verilog. We just heard about COCO2B. So why VHDL? Well, if you look at FPGA design, this is from the Wilson Research Group Functional Verification Survey. They came out and basically have reported that 66% worldwide uses VHDL in FPGA. Okay, and 56% worldwide use VHDL for verification. So that's a big part of the why. So why OSVVM? Well, currently, same study, OSVVM is doing 28% of the market, which is roughly half of the market of the VHDL side of the market anyway. So we're doing quite well there. So what is OSVVM? So OSVVM is a verification framework. It's a utility library that adds to VHDL the language elements necessary to make it a verification language. So give us the capability to do constrained random, scoreboards, functional coverage, requirements tracking. Okay, all that's built into our libraries. We have a rich verification component library, which is one of the places we're working on adding more stuff. We have a scripting library that allows us to do tool-independent scripts, meaning we write a script, it'll run on Aldec tools, it'll run on Siemens tools, it'll run on Synopsys tools. So we're pretty much vendor agnostic on that. We have a co-simulation capability. This was done by Simon Southwell over here in UK, but it allows us to run software on top of your VHDL simulation. So it's a C++ interface that you can run your application code, or you can write test benches and see if that's what you want to do. And then it's a test report capability. So we have a rich set of test reports to help us see what's going when you're running a big regression, to help us see what is going on in that regression. Okay. OSVVM is free open source, and it's developed by the same people, myself in particular, who's helping with the VHDL standards. So we have a long history. So even though we didn't brand it as OSVVM until about 2011, we've been delivering pretty much the same transaction framework, and we've been adding to it through the years. Okay, so through our training, and then we open source basically everything, all the packages we develop for our training. Okay, so when we look at doing test benches in any language, the first step of improvement is going to be using transactions. So if we're thinking just of the interface, we'd be thinking of like, what operations do we do on that interface, right? So if it's a processor-like interface, we'd be doing like writes and reads. Or if it's a streaming type interface, we'd be doing things like sends and gets. Okay. Oh, and if we're doing verification components, we might have directive transactions that tell the verification component to pause for this amount of time. Okay, so the wait for clock is talking to the verification component directly, not having any interface implications. Okay, so if we're not using transactions, we're typically doing signal wiggling. Okay, and this is time consuming, it's tedious, it's error prone, and the big issue is one code error or one spec change, your whole test bench is broken. You got to go out and fix hundreds of sequences, and it doesn't go easy. Okay, been there, done that, don't want to do it again. Okay. So transactions, the thought of transactions is just call a subprogram. Okay, we're not going to worry about what's behind the scenes just yet, because it can be a number of things. So we call procedures to initiate the transactions. It's less work, it's more fun to do things this way. Okay, benefits, it becomes readable, not just by the verification team, but by the hardware team, hopefully also by anybody who writes code. So the software team should be able to read it. The system engineering team should read it. A lot of us are on teams who subject them to coming to the reviews. Be nice to get something out of them, right? If they're going to sit there and be tortured by reviewing what we're doing, it'd be nice to say, hey, you forgot to do this. So that, you know, are you testing this? And you're like, oop, and you can go get something before you run into it in the lab. So this is really the first step to improving your test bench. Now, one very low-level primitive implementation to this might be to put the signal wiggling just encapsulated in the subprogram. And this is indeed a good first step, but we can do better. So we're going to investigate. The downside of this is we get absolutely no concurrency. Okay, so if you want concurrency, which I think all of our verification components do, in particular, you want concurrency if you're doing state machines, because in RTL code, we're used to writing state machines with a particular pattern. Be nice if verification used that same pattern rather than introducing something. Yeah, this is a new cool way to do it. Oh, that's just tedious to learn something for no reason. Okay. We also have some interesting issues with the CPU rec here because it has multiple drivers on it. Okay, and we have some magic behind the scenes in OSVVM in form of our resolution functions that we use that allow us to do this. Okay, so what do we do as far as assembling this together into a test bench? Okay, well, we could just surround the DUT with processes that call these transactions. And basically my theme when I'm doing stuff like this is that there's one process per independent source of stimulus. Okay, so one process typically per interface, although we think of it as one interface, but there's really a transmitter and a receiver interface there. So now the limitation to this one is if the DUT interface changes and it's a non-breaking change for the sequences in here, the processes that are driving the interfaces, well, still we're going to have to change every test bench anyway, because we instanced the DUT here. So we want to get away from that. And so what we can do is we can refactor everything that's driving interfaces into a separate entity and architecture. Okay. And then our test cases become architectures of this. And so now we're a little bit more immune to what's going on in a DUT test harness. Now this is kind of assuming that we're implementing the transactions as subprograms. Okay, that we're doing the signal wiggling as subprogram calls. That's not what OSVVM does. OSVVM likes using verification components. Okay, so we have verification components that translate a logical sense of what do I want you to do? I want you to do a CPU write at this location. So that's what test controller thinks in, and then the CPU model translates that into waveforms. Okay. So now our test sequencer, that has all the subprogram calls in it that we saw on the previous slide. And just like we saw on the previous slide, each test case then is a separate architecture of this test control. And I was just asked this the other day. Yes, I name them all test control. But what I do with my test benches then is each different test bench is in a different VHDL library. Okay. And in OSVVM scripting, we make using libraries easy. Okay. So the benefit then of using verification components is we get concurrency. And we can get, well, that same state machine pattern that we use for RTL design hence making everything more accessible to a wider range of VHDL engineers. Okay. So we look at the framework. It's not OO based. Okay, that's what System Verilog does. Is OO. They reinvent how to make a netlist. Okay, we don't want to do that. This just plugs together, just like RTL. Any engineer right out of school can do test harnesses. Okay. So we instance the DUT, we instance our verification components, and then we instance our test sequencer. Okay. And again, our test sequencer is what we saw, test control with all the transaction calls in it. This is a specific order. It's about VHDL 2008 and external names. So we always do test control last. We always do the DUT first. That maximizes your capability with VHDL's external names or our hierarchical reference capability. Okay, so if we look at the pieces of our framework then, we have our transaction interface, and which is the URTX rec, AXI manager rec, and so on. And then we have the procedures, the transaction API. Okay, so that's the first piece we want to look at real quick. And then making verification components. Okay. And then our test sequencer. So in this presentation, we're going to take a look at all of these little pieces as we go. Okay, so first, the transaction API. It's basically a record. Okay. So, and if you've ever used records as in-outs of your designs, you'll know it's frustrating. Okay, because it has multiple drivers on it. And again, the way we work around that is the types. We're not using standard logic vector. We're using standard logic vector. Underscore max is the resolution function. Underscore C is working around some vendor issues. So underscore C is a notation we took up in VHDL 2008, which means we're running in a compatibility mode for some vendor who hasn't implemented a particular feature of applying resolution functions. Okay. And the good news is they have recently, but the bad news is OSVVM tries to support vendor tools back at least 5 years. So it'll be some time before we switch out of these, but it doesn't matter because our long-term plan is to migrate to VHDL 2019 interfaces when we can get the vendors to implement that. Okay. So, and it doesn't change the record at all. It just requires the addition of a mode view, which is basically a declaration of what direction things are. Then our transaction API is just procedure calls with named for what we're doing on the interface, like read, write, and that kind of thing. And they're not doing the signal wiggling anymore. Okay, so what we proposed earlier, that's not what we're going to do here. Instead, we're just going to say, hey, what do we want the verification component to do for us? We're talking to it abstractly. That's really cool because as you're testing through your multiple different levels of your design, you might plug in a different verification component that does different signal wiggling, depending on whether you're talking to the RTL or the chip level. Okay, so just by changing that verification component, we should be able to run the same set of sequences against it. Okay, and then we call this request transaction. This is how we do our handshaking. It's through these particular record fields, the ready and the ACK. And it just tells the verification component, hey, I just put something in there for you, go do it. That's all, it's pretty simple stuff. And we've used different handshaking schemes through the years. We're now doing integers, and I like that, but that's not important. Okay. And then we get our results. Okay, our safe resize is to translate between the types and to resize things, which is a frequent thing that we have to do anyway. Okay. So independent of verification component, we put stuff into the record. We tell the verification component, hey, go do something for us. And then potentially we get results back depending on the operation. Okay. Most of the operations like this one, they're blocking, they don't do it. They wait for the verification component to finish. But that's a matter of the policy you implement in the verification component. Okay. In addition to these, we have asynchronous operations, which is say, go do, and we don't wait for them to finish. Okay, so if we take a look at a verification component then, we have the AXI4 manager here. We have the DUT interface, which we happen to do as a record. It was a struggle to get the tools to implement to support all the capability of that because there are on-constraint arrays in that record. Because the AXI interfaces have to be configured But it turned out to be, after getting through that struggle, it turns out to be a good decision because there's a lot of things that aren't used in that record, and it makes it easy for people who are using it to set it up right. Okay. And then we have our transaction record. This is part of the transaction interface. Okay. And then building a simple blocking verification component is nothing more than at the top of a process. This can be a single process entity. Wait for transaction, and it says, hey, wait until we get a request. And then when we get a request, grab things out of the record to determine what transaction we want to do, and then do the transactions. Now here I kind of suggest it could be done with subprograms. I don't commonly do that. I commonly just do the signal wiggling here. Okay, I think this is the point of authoring code, but it's really up to you how you want to do it. Okay, now AXI interface is not a simple blocking interface. Okay, so AXI takes a lot more because of the each interface, the split transactions in each interface run independently of each other. So we're actually, instead of doing this, we're feeding stuff out to separate handlers. But generally, if you're writing your own verification component, we always start with a blocking verification component first, because with a blocking verification component, we can verify all the internal stuff of the design. We need more advanced verification components to test the interface capability. Does it comply with, hey, write data can actually arrive ahead of write address? That's weird, but it can happen because of the connection networks and stuff. So does the subordinate device that you've written support that? Okay. Now, an observation I made quite some time ago, but we didn't have the time until the shutdown and COVID was actually very good for us. Because it gave me time. I wasn't traveling all the time. And one of the things that I observed in the past was, hey, some of these interfaces all do the same thing, right? They all do like address bus or memory mapped interfaces. They all do read and writes. Streaming interfaces like AXI Stream or UART, independent of what the transport medium is, they all do things like send get. Okay. So for these interfaces, OSVVM library, the model independent transaction library, has predefined a transaction interface and a transaction API. Okay, this means that you don't have to do that aspect. Okay. So basically then for the address bus, we create a record, just very similar to one we saw previously, except a few more stuff in it. And then we support a basic set of operations. This is a very minimal subset of that. So write, read, check, but also bursting operations, also asynchronous operations. Okay, if it doesn't have the word async or try in front of it, it's a blocking operation. And we do the same thing. Okay, we create a record for it, and then we have our transactions layered on top of that. Okay, so why do we do this? Well, we cut out two of the steps that would normally be associated with the verification components. Okay, and then you can focus on just writing behavior. How important is this? Well, in our training class, when we do an AXI Stream lab where we have everybody write the AXI Stream transmitter and receiver. Prior to doing it, prior to having this model of independent transactions, people could pick one and do one. Now they do both in the same amount of time. So that's pretty good. We accelerate test case development because whether you do an AXI Stream or UART, they're using send and get. And they're using the same record type. So if you wrote something to do, well, let's think something crazy, do Ethernet over AXI Stream or do Ethernet over UART, yeah, you can use the same sequences to play it against either interface. Okay, so we're kind of interface agnostic, hence we can share higher level programs that we run. We support co-simulation with software. So, and it supports anything that uses the model independent transactions, supports, yeah, you can write your test bench in C instead. So the part that we call test control here at VHDL will be replaced with a part in C that does that instead. We accelerate documentation because we've already defined what the transactions are. You just have to have a table. This verification component selects supports these transactions, and then refer off to the user manuals. Okay. And again, we have all our documentation. It's in PDF. It's good and bad. I like PDF, but the younger generation seems to like HTML. So, okay. Okay, so again, with the model independent transactions, writing a verification component is no harder than a procedure. So where System Verilog has their easy approach or their light approaches, we don't need that in OSVVM. Because our main approach is our easy approach. Okay. So if we look at our test sequencer then, on the interface of our test sequencer, all we have is our transaction interfaces. Okay, we have reset on there right now. That's kind of a crutch that will eventually go away. We're going to make our reset verification components or reset procedures talk to some global signals that tell us if anything's in reset and if everything's in reset. Okay. So what an architecture of this looks like then is it has the whole test in that file. So we look at the big picture of things. We have a control process that initializes and finalizes the test. And then we have one process per interface. You don't have to do it this way, but if you're using anything that's a blocking transaction, you do. Okay, and I prefer to write blocking test benches, but we do have a whole, if your verification components implement it, we do have a whole set of transactions for asynchronous transactions. Okay. And then our tests are just calling them transactions. Now, this allows us to write any form of our test, directed, constrained, random, scoreboards, functional coverage, all can be added in here. From time to time, we're going to need to do synchronization. We want two test cases. Once they get to this point, we want them both to run and kind of start up beyond this point at the same time. That we do with our wait for barrier synchronization. So we're doing it here at the start of the test because maybe the AXI manager sets things up before we start throwing things down to the UART. Okay, so the UART has to wait until the dot has been set up. We also synchronize our completion. So we wait on this test done flag. As we're running our tests, we're calling OSVVM capability to check errors and log the errors against our alert log data structure. And end of test reports it. Okay. So a test starts with our control process. And we set up the test name. We'll open up our transcript. Transcript logs everything that you print in OSVVM. No matter where you printed it from, we have a file identifier that's in a package, and you can just use that. And then here we're constructing a number of our data structures. So a lot of our data structures in OSVVM are singletons. That means the data structure is not created right here in this file, but instead is created out in a package. It's kind of weird, but with protected types, we can do what other modern programming languages do. And we also have messages, so we can turn them on and off. So this is turning on a couple messages here. And then we're waiting for the test to finish. Okay, so wait for barrier test done, but we also add out in here. This is basically a watchdog on your entire test. So if your test doesn't finish in 5 milliseconds, it says time to wrap it up. Okay. So that's nice because if you're running a regression overnight and you've queued up 100 different tests to run, okay, and one of them hangs, it doesn't tie up your simulator all night. Okay, it completes, wraps up, and the other ones get to run. All right. Okay, so our test case then is we just call transactions. We have two sides typically. We're sending things into the DUT, and then the DUT does something, and maybe it sends it back out the other port. So we'll do a get on the other port. Maybe we're expecting this, maybe it's just a router inside of our design. So we're expecting to receive the same value. So one of our check functions is affirm if equal. Okay, and it just basically does the received value match the expected value. Okay, another one of our checkers, this one's a transaction, it's passing the check down to the verification component, saying, hey, I want you to do a get, but I also want you to check it. Okay, so that's what this one's all about.
Do you have any predefined kind of queue functions, or would you have to implement that yourself?
We have FIFOs, yeah. We have
Yeah.
FIFOs and scoreboards and that kind of stuff. Yeah, absolutely. Yeah, you don't want to define it as a user because we do it inside of a protected type and then we wrap it with a singleton data structure. And the advantage to that is the user never has to, the test bench writer never has to mess with the protected type calls and that kind of stuff, which is messy.
The affirmative equal, that's part of OSVVM.
Yes, it is.
Is there ways to kind of mask certain fields in a transaction, in the transaction or the record? And ignore this one, ignore that one in these situations?
This is, yeah, you would have to break it out individually but you can overload anything you want to overload. So you could, we also have an affirm if that doesn't do the equality check yourself. It just takes an expression, and that expression could be a match function that you write that does that. And we have that same capability with our scoreboards. You actually pass your match function into the scoreboard to determine what does equality mean. Because in a UART, when you get a break error, when you're injecting a break error and you receive a break error, you care less about the data. So what you're asking about is absolutely required capability that we have to have. Yeah, and when we call this, we're using a ID-based methodology here, and the ID-based methodology allows you to track back to who done it. Okay, well this is coming from this TV ID up top. Okay, and we get a path, a very clear passed or failed message. The failed message is automatically enabled. The pass message you actually have to enable with the set log enable. Okay. Benefit, we get improved readability because we're using the transactions, and the self-checking should become pretty trivial. Okay, other than you're thinking about what the match functions have to be and all that. Yeah. But it allows you to think at a higher level. So wrapping up, coming back to the control process. Okay, so the first thing we check is, did we time out? Well, now is a VHDL function that returns your current simulation time. And if now is greater than your timeout, then you timed out. Okay. And we close our transcripts. We have this affirm if transcripts match. We have a particular naming pattern for the transcript. It's basically testname.log, although you can set your own up if you don't like that. You can name them yourself in that transcript open, but then you have to go through a little bit more verbose call to verify your transcripts. If you want to, verifying your transcripts is important to you. It is to me because a lot of what OSVVM does in the libraries, checking the libraries and stuff, involves outputting stuff and making sure it's staying the same as it used to be. We have a get affirm count that tells us how many checks we've had. It's pretty much inappropriate to say a test passed if you didn't get any affirmations. Okay. Then we're checking the coverage. So we have functional coverage, and I'm not going to talk about that today, but I've talked about that. We have a lot of online presentations if you want to have more depth. Okay, and we're checking the alert count. And that's probably because this is a requirement. It's more of a requirement thing. We'll talk about that in a minute. And then we're doing end of test reports. This causes a flurry of reports to be generated, which we'll talk about at the end of this today. Okay, so one of the big problems with our testing is we don't effectively do reuse enough. Okay, because historically, what we've done is we've written an RTL test bench, and we've written a core level test bench, and we've written a chip level test bench, and they're all similar, but slightly different. And each one as we go is slightly more sophisticated. But if we're thinking at the waveform level, we're creating custom waveforms for each one. If we're thinking at the transaction level, the test cases are very similar. Okay, and we should be able to get some more, if not direct use, easy to port test cases going. Okay, so we like to use the same structure for everything, whether we're doing a small RTL or unit level test, or whether we're doing a core test or a full chip level test. I like using the same transaction-based structure. Okay, so where I start is I start looking at the chip to identify reuse, because those verification components that I need to test the chip with, they're must-haves. When the project is done, I'm gonna have those. So knowing that I'm gonna have those, then I go and look at, okay, I need to really start with the RTL test. But planning has to start at top level because maybe I can reuse these things at the lower level test. And I want to reuse these things as much as possible. I want to structure my verification to know, well, the chip has to do this. The core probably has its own verification components that you need because every RTL cores tend to have to be standalone tested also. Okay. Knowing that, then I want to reuse any of those I can in the RTL tests, in the unit. Okay. Same thing about test cases. If I break my test cases down into transactions, if I can reuse my transactions or do a small porting, yeah, I have to add this code and this code around it. And then what I want to do is back porting, which is add to these other verification components when I'm running at the lower level, make them be able to run the system level test just by ignoring the transactions that aren't for it. We may be able to get some reuse out of the test harnesses. I haven't focused on this too heavily. I've toyed around with it some, but the test harnesses are a net list and they're a matter of hours of investment. They're not days of investment. So it's not a big win, but yeah. But I've also found that by copying and creating additional test harnesses, sometimes I can solve some of the configuration problems of VHDL too. So like we have 2 variations of AXI stream, 2 variations of AXI full, but internally they're the same thing. It's just the IO that's a little bit different on the 2. So by using 2 different test harnesses, we're able to run all the same test cases just by keeping everything, the names consistent throughout both separate test harnesses. Okay. Yeah, so we can maximize, by using that same structure, we can maximize reuse. If somebody's pushing well, I should do procedures, start with procedures and then switch to verification components. Now you got 2 different test environments. You're going to get very little reuse between those. Okay, so the next capability, and this is something you can use without using anything else of OSVVM, is our alert log capability. And then in there, we have our messaging, which we call logs. And this is all about how do I turn things on and off, right? When I'm debugging, I want a lot of messages to help me debug. And otherwise, though, I want to generate pass-fail messages. Very, very terse messaging when I'm running regressions. Okay, so that's what that capability is about. Error tracking. I didn't know how bad I needed error tracking until I had it. Okay, because before this, and we'll see this in a minute. I guess I won't jump into it now. So basically, if there's an error, print a message. Otherwise, count. Okay, count and count the error. Not otherwise, but and count the error. Okay, so self-checking. That's our affirmations. Okay, we already saw that. Creates a pass when we pass. Creates an error when we fail, and counts the errors. Okay, and counts the number of affirmations done. Because that's a quality check on your test. If I get to the end and there's no affirmations done, yeah, that's not a good thing. Okay. Historically, we've been printing past even when we get 0 errors. We're going to change that. Okay, so you got to get 0 errors and you have to have affirmations to get a pass. We're going to then it's going to be no checks or something like that is what we're going to produce. Then we have a transcript file to collect everything that OSVVM prints. And you can print to that same file. Okay. Not anything that we printed. So why do we need this? Okay, well, before I had this capability, what I was doing for self-checking was an if statement and then perhaps a report statement to say, hey, an error happened. That'll print out on your screen. There's an error happened. But now I also have to track the counts because that tells me pass-fail, right? I got to know pass-fail. All right, so then when I get done in my test control or in my control process portion of my test bench, it's got to go out and collect all those errors. Did you remember to get them all? Yeah. There's some nights that remember late at night. Yeah. So they can drive you nuts. So were all the error sources included in the sum? Well, with OSVVM, this is going to be really easy because we're building a data structure. First, the messaging though. So logs are about conditional printing. I say log and some message, and I can include a level with it. So here I'm including this info level. We have levels always, which always prints, debug info final pass. These are just categorization of what the message is about. Okay, so info is the model wants to tell you what transaction it's doing. Debug would be details on every little aspect of that transaction, especially relevant if you have a split transaction interface where the right address and the right data come out separately, and then the right response comes back, and you want to know all about all of that. Okay, so they're disabled by default. You've got to enable them with the set log enable that we show up there to turn them on. So if we run the code sequence above, the first info message doesn't print because it's not enabled yet. It's only the second info message that prints. Okay. Error tracking. Okay, so error tracking, we have the affirmatives which track errors, but we also have alerts. So the difference is alerts are just for things that are not self-checking. So something bad happened on the interface. We have a RAM, and the old RAMs that had a shared data bus. What happens if output enable and write enable are asserted at the same time? Okay, well, if that happens to the real board part, very bad things happen, like disruption of the entire memory. Okay. So we want to check for that. And the cool thing about checking for it in VHDL is if it even glitches for a delta cycle during the VHDL simulation, we'll find it. And here we have levels also. We have failure, error, and warning. Failure is the default. We can set up different aspects. We can set the stop after a certain number. We allow an infinite number of errors to happen at this point, but you can trim it down. OSVVM, I want to see a reasonable number of errors because I write bigger test cases and I want to see what aspect failed. And if I can't flush out more understanding of that error by collecting more error messages, some people have a different philosophy. They write different size tests. So if you've seen other approaches, they like stopping at 0 errors. That's fine. We can set that. Okay, and I think we're going to set some we have some new configuration options that happened in the 2403 release. I think we're going to make that configurable too. Okay, we have the print count, stop printing after a certain number. The thought there is if you've got something that you don't want to pay attention to, but you still want to see its error count, you can tell it to stop printing. Okay, and then we can turn alerts off, but we rarely, if ever, do. Should you turn one off, our reports won't let you forget that you did that. Okay, because we track independently of whether it's a real error or not, we track disabled errors. We assume that VHDL is used in a safety critical environment, and we try to make it so that if you task your admin, check these reports, I want to know that there's no disabled errors, alerts in it, they can search it and find it for you. Okay. We've already talked about affirmatives. This is just the same thing with read and write instead of send and get. Okay. Transcripts. So again, all of the OSVVM printing goes to a file object named transcript file. If it's open, if it's not, then we print to output, just the console window. So generally, this is kind of an update. We set the test name first. That's something we actually OSVVM requires you to do that. Okay. And if you've done that and you say transcript open without any parameters, we'll open that test name.log. You can also give it a file name parameter if you wish it to be something different than what OSVVM defaults to. And then at the end, we say transcript close. Okay. If you're debugging, maybe you want it to go to the file and go to the console so you can turn mirroring on. We have a simple print that'll print to it. We also have a write line defined that'll allow you, if you like text.io better, fine, use text.io. Okay. By the way, that simple print, yeah, I don't see it show it here. I've shown it on my other presentations. VHDL 2008 2-string works really well with that. Okay, so if you don't like text.io and you're printing, look at 2-string. Anyway, basic reporting. Right now, we're doing done fast, done passed, and done failed. But again, we're going to add some more completion messaging to that. So if there's no checking, we're not going to give you a pass anymore in our reports anyway. Okay, so again, make sure you're setting up the test name. Otherwise, OSVVM will use a default name. You don't want that. Okay, and your test cases will probably fail. Okay, when in our reporting level. Okay, so message categorizations. We have some message categorization in the form of the levels. Okay, but how do we differentiate different sources? And particularly, how do we handle a situation where one interface, like a CPU interface, might be generating an infinite number of messages, and the interface you're debugging, like a UART, is infrequently generating messages. So what that tells us is these little levels aren't enough. Okay, they're not enough. We need to control messages by source or by group of sources. Okay, and I've seen other ways of doing this. So string-based. But if you use a string base, then you got to look up that string every time in your data structure, and that's going to be slow. Okay. We could use enumerations. I've seen another approach that does that. That really isn't even a library anymore because everybody's editing the enumerations to add different things to it. That's not going to work so well. So what we do instead is what I call ID-based. And ID-based, we're going to have an ID associated with different levels, different classic categories of messages. Typically, a verification component is going to have its own ID associated with it. So, like for example, if we have an ID, we might set it up to be the instance label of that verification component. That's usually how I set it up. And we could manually enter that into the verification component. That's not how I do it. Instead, we can use a VHDL attribute path name. And actually, if you use the entity name, tick path name, that'll give you the path down to that entity. And then we just strip it, the tail of that, and the tail of that is the instance label. Okay. So that's how we get everything in OSVVM right now. Actually, we've added a few extra things to that. If you look at some of the stuff we've done in the library, you'll see it there. Okay. You can set up child IDs. So these are subcategorizing the CPU model. Okay, maybe into data errors and protocol errors. And then we relate that back to the parent ID. So it reports in a high chance that. Okay. We do the new form of producing the reports. We justify everything. So keep these names short. Otherwise, you'll have a big space gap on some of the prints. Okay. Everything we've talked about so far, alert log, affirm if equal, set log enable, set alert enable, all takes an ID as a first parameter, as well as not. Okay. So you can, for simple things, you don't have to use IDs. Okay. So for very simple test benches, we don't do this. But as soon as you start adding verification components, you have more complexity. You want better trace back to who done it. So yeah. Okay. And then when we do this, it gives you the ID of who did it. And if you had a child ID, it's going to give you the parent ID : the child ID. Okay, so the trace back is really good. So that one of the guys was talking about earlier in the presentation. Debug is 70%, right? That's what their statistics were. I think the Wilson report, I think, said it was at least 50. So this is important to be able to track things back to who done it quickly. Okay. So with ID-based reporting, we give you a little bit better reporting. Okay. If you fail, we're going to track back and show you who done it. Oh, and I failed to update this slide. The numbers you see up top aren't consistent with the table anymore. So. Requirements. Requirements in OSVVM are alerts that we create by calling get rec ID. Okay, and it's the only difference between them is we do a little bit better, more tracking and more reporting with them. Okay, then we have our affirm if equal. So affirm if equal can take a rec ID and we can check things. So we can use the same things we use for the requirements. Now, one of the things I notice about requirements though is often there's one place where we check a requirement, not multiple places, but one. So creating the ID for that is just extra overhead. And we can skip that for requirements in particular. So if we just give it a string name first, It's going to use that string name to create the requirement and then log that as a requirement. And if it's the only call, I think this is a little bit better because it gives us a little bit better what is rec ID 1, but we have to go back up and look if we want to correlate, right? But here it's directly correlated. This is reporting against this. Okay. Okay. So end of test reports is going to create YAML reports. And that's going to generate our requirements reports. Okay. And requirements are affirmations. So a failed requirement is indeed a test failure. Okay. So you only have to write the check once. If you checked it as a requirement and it failed, the test fails. Internal to the alert log package, you don't need to know this, but inside there, it's a package that has a protected type in it. Protected types allows us to create variables inside of that data structure, and hence we can build things. And all our IDs are is we have a name, and when we give an ID back, we're just really giving back an index into this table. That's all. It's not that complicated. And we can look up the IDs from other places. So we can do get alert log ID, and we can do find alert log ID. We'll typically do that on our sequencer. So we'll set up the ID in the verification component, and then the sequencer, if it doesn't know it, you can look it up. Okay. And again, good data structures allow us to do really good reports. Now, before we get to the reports, to get the reports, you've got to be running OSVVM scripting. And OSVVM scripting is a procedure layer that runs on top of Tickle. So if you load the OSVVM scripting environment and you have a script that just wants to run Tickle, you can run that. There's no problem of running other scripts within it. It still runs any tool vendor script. But this is simple. You want a library? You say library and then the name. That will create it. That will also make it the current working library. This is more in line with what VHDL says, because then when we say analyze, we're analyzing into that working library. You don't have to specify anything on the command line. Okay. And likewise, when you say simulate, we're still using that top library we just told it about. Okay. So it's simple, like a list of source files, except we get the power of Tickle if we ever need it. You may never need Tickle on top of this. Okay, we use it a little bit in OSVVM, mainly to work around quirks in the tools, because we want to maximize the number of tool vendors that support OSVVM. Okay. So again, this is all about one script API for any simulator. We support GHDL, NVC, both of Aldeck tools, both of Siemens tools, Synopsys, VCS, Cadence, Excellium. And on these tools, if you find something not working, just file a bug report with OSVVM, or you're also welcome to send me an email. Okay. So one of the things that's been on my mind is how do we run a ton of regression simulations overnight? Well, commercial simulators have a superior debug environment. They're good for debugging during the day, but if you're just doing self-checking, you can run those tests with an open source simulator and have an infinite number of licenses. Okay. And both GHDL and NVC are very respectable simulation capability. They're not as fast, but it doesn't matter when you can buy a whole set of servers and stuff. Okay, so our reports. This is kind of a laundry list of the reports we're going to take a quick look at. So when we run a regression, the first thing you're going to see is what I call a mini build summary. It's just after all those test duns of each individual test and all the spew that the rest of the test case puts out. Then when we finish, we're going to give a report, and it's going to say build error or build passed, and it's going to tell you the build name, and then it's going to give you some specific number of tests that passed, number that failed, and so on. This is the indication that tells you have to go do something. Okay. Next, we create a build summary report. This is created in the directory you're running your simulation in, but you can also say open build HTML. O, B, and H are all uppercase. Sorry, I'm a fan of camel case. And it will open this report for you. And in there, it will give you your simulator transcript log. So we take that and put it in a special place. We also make an HTML version of it. So by default, we make an HTML version of it. If you're a person that likes scrolling that report, you can scroll an HTML version that's 180K lines long. You can't do that with a text version, or you can, but it's going to take a lot longer. Okay. Then if you're running with requirements, you'll have a link to the requirements reports. If you're running with the tool vendor's code coverage, you'll get a link to that. But that's just, we're running their tools, producing their HTML report, and merging everything and giving it to you. Okay, so it takes really the tedium out of coverage collection. I used to hate doing code coverage, and now it's just no big thing. You just turn it on and it's on, and you're good to go. In there, we have a test suite summary. So we break our tests down into test suites. So if you think of like OSVVM, we have a large library of things. So we have like AXI full, AXI stream tests. So all this is doing is categorizing our test cases. It's not that unique, but then we give a summary of it. And then we give our test case summary. Okay, so you run a regression overnight, you have some failures in it. How do we find things? Okay, well, up top, you see that it failed. You would have seen that already in the mini report too. And then you come down to the test suite summary, you find out which test suite failed, and oops, pardon me. And then you go down and find the test cases that failed. And then everything that's blue underlined is a hyperlink. So then that links you down into the test case report. Okay. And we'll see the test case report in a slide from now. This is our requirements report. If you have a requirements in more than one test case, it will merge those and sum them up. Okay. This is our test case report. So our test case report has links at the top. I think the first 3 links there link the stuff in this report, and the other ones link the stuff outside, like your transcript file. If you did a transcript open during a test, we know we've logged what file that was, and we link to it. And we have a link into the HTML transcript window. The importance of that link is we have HTML tags for each test case in that file. You click on the link here, it goes to that HTML tag, immediately opens the report so you can see what's going on. I'll show you an example of that inside. Okay. And then we have our alert report, our coverage report, functional coverage, and then our scoreboard report. Every scoreboard FIFO you use in OSVVM, we give you the statistics for it again. Okay. So our test case report, we have a setting for the alerts. We have settings, and we have test cases. This is for one that's failed. So you can see here, failures show up in red. They show up in more of a red in your normal screens. Okay. Then our functional coverage report. Well, one of my goals of all this reporting stuff was we were getting picked on by one of the vendors. And they were saying, look at our functional coverage reports, look at their functional coverage reports. And I realized they were right. And we had to do something about ours. So the HTML is our answer. We've got something as good, at least as good as what they're doing now. So the System Verilog guys were saying System Verilog is better because, well, no longer. So. And then our FIFO scoreboard report. This is the number of items that have transmitted through it. This is the number of items that popped. If you're using it as a scoreboard, these ones were scoreboards. We can tell because that's the number of items checked. Okay. Our HTML transcript file. One of the things that we do is if there was an error during a given simulation run, we factor that error message out and put it in the report in red so you can see it. So if you're to type that, I hate those HTML things, other HTML things, tables, I want to scroll the report. Fine, do it. And you can find things pretty quick doing that too. Okay. Then I mentioned if you clicked on an error in your test case report, all of those, I should flip back, all of those triangles you see here are HTML summary tags. You just click on them and they'll reveal what's underneath them. So there could be many messages under there. Okay, and this is an example of that. This is ALDEX output. And we deliberately made a test case fail so that we could see the messages in it. Okay, so this is what it looks like. Okay, we're kind of wrapping up. Getting OSVVM, it's on GitHub, but it's also osvvm.org. If you register, you can get a zip file if you prefer that. If you do register, it's a manual human process of approving so that we keep out spammers. So if you don't get approved right away, send me an email. We can make sure it happens. And especially this, I'm out for 3 weeks right now, so it's a little bit harder to get to those things. Then to run things, this is from within your simulator window. If you're right at the directory, if OSVVM libraries is at the same directory in Tickle, you can say file make dir, and a simulation directory, change directories to that. I always run my simulations out of a particular directory that only has junk in it, any simulator output, so that, you know, when things are ugly and that kind of stuff, we just delete it and recreate it. So it makes cleanup really quick. We source the OSVVM startup scripts and we build the libraries. When we source the scripts, we remember to path the OSVVM libraries. We put it in this Tickle variable OSVVM libraries. So you can just build OSVVM libraries if you just do that. I kind of giggle at vendors these days because they've been saying, like Siemens has been saying, oh, if you use this new QRun thing, you can compile these 20 files all in one command. You just load in this list. I'm like, how much difference does that make? So this is my answer to that. We right now are not doing that. We're thinking about it. We're thinking about creating that capability, and it wouldn't be hard to implement. Compiling all OSVVM libraries, depending on your simulator, depending on your compute platform, 20 to 60 seconds. So hence, not too hip on, you know, adding that capability because it's not a big win. Yeah. Okay. And then you can run all of OSVVM tests or there's a run demo test that'll allow you to run just a limited set of stuff. You want to see that one runs our whole regression suite on the publicly available regression suite. So on all the verification components. Our testing of our utility library is private. We don't distribute the test for that. But if you're doing something like DO254 and you need that, we can talk about that under NDA. Okay, so OSVVM basically gives you everything you need. It's a complete solution to your verification. We give you the framework, the utility library, the component library, which again, that's one of our places we're working on. Our script library, co-simulation library, and our test report capability. What we've tried to craft is something that any VHDL capable engineer can do. Okay, and that you can move people around. You don't have to have specialists. You can have specialists for the duration of a project, but move people around from RTL to verification tasks. All you need really is a good verification lead. Because as you heard this morning, the fun stuff is writing the verification components. The hard stuff is the test plan that a verification lead has to do. Yeah, definitely concur with that. The other big thing, OSVVM, as I mentioned with the alert logs, you don't have to be doing any other thing in OSVVM, so you can grab things incrementally and learn as you go, okay, and deploy things as you go. Okay. We have time for questions, if anybody has questions.
Functional coverage item you've got there, is that things like bins and coverage that you get in system very long?
Yeah. So the way we do it in OSVVM is just like with the alert log package, we're building a data structure in a package. We have a coverage package, we're building a data structure in a package. And each thing that we grab becomes a coverage model. And then you can create bins within that coverage model. Yeah. Then, yeah, with that report slide I showed, we iterate then because everything's out in the package and it's in a data structure, we can iterate the data structure and produce reports.
And can you interrogate that dynamically so you can steer your randomization?
Absolutely. Yeah. So that's By the way, that's a capability that System Verilog doesn't have, right? Or did they add that recently?
No, I think I thought you
Uh,
could.
Okay,
It's not built in, but there are ways.
okay, yeah. Yeah, most of the stuff I've heard about System Verilog, they're doing all the coverage-driven randomization. After you finish the run, let's pick another better seed set for the next run.
Within
But
it, you
you-
can, but it's not built into the system.
Right,
There have been papers written on how to.
cool. Yeah, kind of like that. Other questions? How many people are already using OSVVM? Okay, yeah. Good. Well, thanks everyone for coming.
Thank you. Thank you.
Maybe we have a